Okay, good morning. Uh, we continue the lesson. Today's topic is the equation z to the n equals to w. But let me also tell you that tomorrow we don't have any classrooms for Math 4 apparently, because Sima is going to take this classroom and then they couldn't find any classroom for us. So this means that you need to sit down and watch the video yourself tomorrow, somewhere in the library or whatever. I just want you to know. But Math 5 is also, Math 5 is actually the same time we will have. Yes. Okay. So I finished. I will teach you this lesson. The next lesson, I recorded it. It will be uploaded in 2 or 3 hours, and then you are supposed to sit down somewhere tomorrow and listen to that lecture. Okay. Okay. Let us now start today's lesson. So we want to solve this type of equations in which n is a natural number, of course, greater than 1. I will tell you why. And w is a complex number. N is given, w is given, and then you are supposed to solve this equation. Solve means find all of them. And even though I told you this is in natural n, of course, it makes sense if n is greater than or equal to 2, yes? Because if n is 1, of course, z is w. There is nothing to find. But if n is greater than or equal to 2, then it becomes more interesting. So this is an important problem because it opens the way in front of us to talk about the nth root of a complex number. Because in principle, if I ask you x to the power of 5 is equal to a, do you know the answer? When you are doing in Math 1c, then x is the fifth root of a. So you can also denote it by this. So this problem in the realm of real numbers was very connected to the fifth root, to the definition of the fifth root of a real number. So by the same spirit, this more or less paves the way to talk about w to the power of 1 over n, or sometimes people show it by the nth root of w. So this problem is, of course, an interesting problem in its own right. And another thing that makes this problem important because it enables us to be able to talk about the nth root of complex numbers that we haven't talked so far. Okay, and then the strategy that I want to use to teach you this is just solving numerous examples. So let me summarize what we want to do. An equation of this form is given to you. N is natural and greater than or equal to 2, given. W is complex number. It belongs to the set of complex number given. And my question is that what is all possible values of z? Okay. So how should I solve this problem? Let me give you examples. For example, let me start with a very simple example. Z cubed is equal to 1. I want to solve this problem. Comparing this with the given equation up there, yes, here in this problem 3 is n, which is given. W is 1. Of course, 1 is also a complex number because it can be viewed as 1 plus 0i. So that's exactly the topic of this lesson. We want to find z. Of course, without proceeding, without continuing, you immediately know what answer, one answer at least. What is that answer? 1. Okay, so 1 is still an answer, yes, because 1 is also a complex number. But there are two more answers that are not real. They are complex. We want to find all of them. So the first thing that you do, you need to use the polar form. So you start with a sentence like this. I am looking for z. I would say let z be equal to r cosine theta plus I sine theta. This is a valid assumption because all complex numbers have a unique polar form if we stick to the standards, to the conventions, except of course the zero. The origin, the complex number 0 does not have any polar forms, but that is not a big problem because it is clear that 0 is not an answer. 0 to power 3 is 0, 0 cannot be equal to 1. So when I say let z be this, this is completely, we are on the safe side. Any complex number that is a potential solution to this has a polar form, and it's unique. So I will start with this sentence, let z be this, and then you are supposed to find r, you are supposed to find theta, because if I find r and if I find theta, I put them back here, I find my z, and that is my goal. I want to find my z. So what you do, you put this into the equation, and this formula, do you remember? If I ask you what is z to power n in the polar form, that was an important part of the lesson, and that was the reason we were interested in writing a complex number in the polar form in the first place. The formula tells me this becomes Rn, but in principle I should put n there, but I could convince you hopefully that instead of putting this n there, you can multiply that n by theta. So that is the power of putting a complex number in its polar form. So this is the formula, this is in the formula sheet, and we will use it here. So I put this back here, what do I get? I get r cubed, and then I would say cosine 3 theta plus I sine 3 theta. I am using that formula for the case that n is 3. On the right hand side, I have 1. I should be able to find theta using this relation. Might be there are some alternative ways, but the way that I prefer is to immediately compare the absolute values. Because if this complex number is supposed to be equal to that complex number, then it means the absolute value of this complex number should also match with the absolute value of this complex number. But if I ask you what is the absolute value of this number, what is the answer? What is the absolute value of this number? Hello? So what is the absolute value? Yes? I don't see you. No, this one is 1. But what is the absolute value of this? Well, of course, it is also 1, but on the other hand, it is? No, absolute value is this one. No, I am saying this is a complex number. That's a complex number. Then absolute value of this should be equal to absolute value of this. Absolute value of this is 1. Yes, absolute value of this is also 1 on the one hand. On the other hand, because I want to reach to an equation. So what is the other hand? R cubed. Yes, is that clear? So remember, this is the argument, this is the absolute value of Zn. So absolute value of this number is r cubed. Absolute value of this number is 1. I want to have them equal, so I reach to r cubed equals to 1. But let me do something. What is r then? 1. Isn't it? It seems a little bit stupid, isn't it? Do you feel it should be a little bit stupid or not? That r is 1, because if I can solve r cubed equals to 1, so am I discussing about just the name of the letter or what? I want you to feel that this is not a stupid argument. I am telling you, I want to solve this equation. I am doing all these things, and then to convince you what the solution is, then when I reach to this point, I say that this equation is the same equation, the only difference is that z is replaced by r. Then I am jumping to the conclusion and say that r is 1. You might say, okay, why you couldn't say that z is 1 in the first place? Yes? What? R is not a natural number. R is a real number. Yes, R is a real number. So that's the big difference. Here, if you insist that z is a real number and you want to find it, of course you find only one answer, and that is 1. But I am looking for other possibilities. But in this case, there are no other possibilities because R is the absolute value. Absolute value of any complex number is real. So R cubed is real. And in principle, I should mention that R is real. Then R is 1. Yes? So from these two numbers that I was looking for, R is found. And then what do? You put R equals to 1 back into this equation, then it becomes 1. Then I will get this one equals to 1. So it becomes cosine 3 theta plus I sine 3 theta is equal to 1. Yes? So the first step, write it as a polar form, put it back into the equation, compare the absolute values, then you will get R. Put R back into this equation, you get another equation for theta, and try to solve that and find theta. But then, what is this conclusion from here? I get a system. The real part should match with the real part, and the imaginary part should match with the imaginary part. Yes? But then I have to find a theta because it is a system, but not in two unknowns. The unknown is the same. So you have to somehow reconcile these two in a way that they are consistent. Okay, but that's not very hard because I am looking for an angle whose cosine is 1 and sine is 0. Where is that angle? Cosine is the x-coordinate, sine is the y-coordinate, so that should be here. Okay, so what can I write about theta? I can say 3 theta is my angle, which is 0. Let me write it in degrees. And then plus 360 degrees times n. Yes, and then n belongs to z. So, and I'm looking for theta, so I divide by 3, so it becomes 120 degrees times n belongs to z. Okay, that is important now. How many theta I got? Infinitely many. But be careful. There are infinitely many answers for theta, but not necessarily infinitely many answers for z. I am looking for z. I am not looking for theta. Theta was just an intermediary to find z. You might think R is one unique number. Theta, there are infinitely many of them. So you might think there are infinitely many answers for z, one for each one of the values of theta. But do you buy this argument that there are infinitely many z's involved? One for each value of theta? Why not? Yes, because sine and cosine are periodic functions. They will start repeating themselves. The angles are, of course, all of them are different. I agree with you, but doesn't mean that cosine and sines are also all different because they are periodic function. They will repeat themselves. Okay, and then, by the way, what is the period of these two functions? Do you remember we had it in chapter 2, trigonometry? Yes? Not 60, 120. 300, so the period of this function, do you remember? Cosine of bx, sine of bx. The period was 360 degrees divided by b. So the period is 120. So how many solutions we will get at the end? 3 only. So this is why in principle, you have to assign all possible values for n, but don't do that. Only 3 of them is enough. So, and those choices are 0, 1, and 2. This is not compulsory. You can choose any 3 consecutive ones, but this is the standard one we choose. So if n is equal to 0, what happens to theta? Theta is 0 degrees. If n is 1, theta is 120 degrees. And if n is 2, theta is 240 degrees. There are infinitely many more. but they will not give rise to infinitely many different answers for z, because cosine and sine will repeat themselves. Okay, but now I need to write the answer. So I have three answers: z1, z2, and z3. In all cases, r is 1. So in all cases, I put 1 here. But for the first one, I write 0 degrees. For the second one, I put 120 degrees. And for the last one, I put 240 degrees. So let me explain once more. So you see, if I go one more, it becomes 360 degrees. But when I put 360 degrees, it will not generate a new z. It will generate the same z. But if these numbers are famous, depending on what the problem is, when you can simplify, it is better to simplify them. So what is the simplification here? Cosine of 0 degrees is 1, sine of 0 degrees is 0. So that is what you predicted from the beginning. So one answer is really 1. You got it back. But there are two answers that you couldn't guess. They are complex. But I have them in my memory. Cosine of 120 is minus a half. Sine of 120 is the square root of 3 over 2. And for this one, both of them are negative. So these three numbers are the answers to this equation. One of them is the famous one that you already know about it, but two of them are really new. So these are only three complex numbers whose third power is 1. Okay, let us try to wait. Any questions? If you really want to test it out, for example, take this one. I don't know, multiply it by itself 3 times, simplify it, you will see it becomes 1. Of course, you don't have to do that, because you can use the polar form and raise it to power 3. What happens? This will go to power 3, this will be multiplied by 3, but cosine of 360 degrees is 1, sine is 0, so it becomes 1. So it is already clear that if I raise this to power 3, it becomes 1. Okay, but let me also talk a little bit about the geometry of these points. It's also important to remember. First of all, do you have any questions? Okay, so if I ask you, where are these points located on the complex plane? They have something in common. Do you agree that all of them lie on a circle, on the same circle? And if yes, what that circle is? I am claiming that all these three answers, if you want to find them on the complex plane, will lie on the same circle. What is the center of that circle? What is the radius of that circle? Yes?
So the radius is just 1, because the absolute value.
Yes, the absolute value of all of them are 1. So the distance of each one of these points to the origin should be 1. So it is on the circle whose center is at the origin, and the radius is 1. And they are distributed evenly. That's also good to know. So this geometry of the complex roots, the complex numbers satisfying that equation, is interesting. So where is the first one? The first one is only 1, so it is here. So let me write 1, minus 1, minus 1, and 1. Where is the second one? You can, of course, this is hard to understand it from this standard form. Let us look at the polar form. The polar form, the argument is 120. So where is the other one? So you start from here, you go 120 degrees, and the second one is here. So this is your Z1. Yes. And this is your Z2. But what is Z3? Z3 has the same radius, has the same absolute value, but its argument is 240. So it means that from here to here was 120. And then I go here. So from here to here is 240. And I get this one is Z3. Okay? And then this is important to realize that if you connect these vertices, these roots together, if I do it precise, yes, which I didn't do it, but then you will get a regular triangle, which is an equilateral triangle in this case. Okay, so it is important to know what geometrically happens to the roots, to the solutions. Is that clear? So from this perspective, if you understand this, you could solve the problem a little bit faster, because guessing z equals to 1 is not hard. So you find one of them, and because this is 3, it is guaranteed that there are exactly 3 roots. So you say that 360 degrees the full circle. I divide it by 3, it becomes 120 degrees. So then I start rotating this first one by 120 degrees, I get the second one. I rotate the second one by 120 degrees, I get the third one. So that's also a geometric way of solving this problem. So if you want, you can write this as a remark. If I ask you how many solutions are there, remember exactly n solutions. If this is z cubed equals to 1 or any other number, 3 solutions. If this is z to power 5 equals to 1, 5 solutions. Z to power 6, 6 solutions. Yes?
Are they always evenly distributed like this?
Yes, always. And that is not very hard to realize, because what you get for theta is a multiple of n plus a constant. So it means that that constant, wherever it is, the other ones are coming one after the other. Any questions? Okay, so let us solve another example. So for example, let me write 2z5 is equal to, let us say, square root of 3 plus I. Okay, so I'm not sure about if this is a good number, so let me make it 1 to make sure that it works fine. I don't want to confuse you with hard numerical calculations. So we want to solve this. Okay, so let us try to review something. So how many solutions do you expect? 5, exactly 5. But I have to get rid of this 2 first. So I divide everything by 2. It becomes 1 over 2 plus 1 over 2i. And then you start with this sentence that let z be equals to r cosine theta plus I sine theta, yes? And then you put it back into that equation. Okay, so it becomes r to the power of 5. 5 goes as a multiple here. When I put this back here, I get this equals to 1 over 2 plus 1 over 2i. Okay, do you remember? I have to compare absolute values. This number is supposed to be equal to that number, then therefore the absolute value is equal to the absolute value there. But if I ask you what can I write for the absolute value of the left-hand side, it is just simply r to power 5. And the absolute value of this I have to calculate. It becomes 1 over 2 to the power of 2 plus 1 over 2 to the power of 2. So this becomes 1 over 4 plus 1 over 4 it becomes 1 over 2. Square root of 1 over 2 is simply 1 over a square root of 2. But what I'm looking for R. So I know that R is real. So R becomes the fifth root of this number. But the fifth root of that number is what? Is 1 over the fifth root of the second root of 2. You can leave it like this, but can I write it more simple? More simpler? Simpler. Yes, because this is the fifth root of the second root, it becomes the 10th root, yes? So if you have a root m, another root n, another root p, and then continues, you can write one root in which you multiply m by n by p, and it continues. It's not, of course, hard to understand. Why? Because this fifth root of the second root of 2 means what? Means the fifth root, but this means 2 to the power 1/2. Then this means 2 to the power of 1/2 to the power of 1/5. Then I multiply the powers, it becomes 1 over 2, 1 over 10, and then it becomes the 10th root of 2. So that is why this is true. But here, these are nuances. I don't want to distract you with these. These are numerical calculations. And what was the next step, do you remember? As soon as I got R, I go back to the previous step and replace R with the number I got. But I don't need to suffer to put this there, because what I need is R to the power of 5, and R to the power of 5 is in front of my eyes. So instead of R to the power of 5, I just put that number, yes? So it becomes 1 over square root of 2, and then I will have cosine 5 theta plus I sine 5 theta. Yes, that is equal to 1 over 2 plus 1 over 2i. Yes? What do you think is good to do now? I have to compare, yes? But before comparison, let us get rid of this number there by multiplying everything by square root of 2. So then what happens? It becomes cosine of 5 theta plus I sine of 5 theta. And then it becomes a square root of 2 over 2 plus square root of 2 over 2i. Yes? And now I have two conditions to satisfy here now. So one of them is cosine 5 theta should be square root of 2 over 2. The other one is sine 5 theta should be square root of 2 over 2. So what should be 5 theta? These are famous angles. They are related to 45 degrees. And both of them are positive. The same angle, sine is this, cosine is this. So definitely 5 theta is in the first quadrant. And it should be what? 5 theta. So be careful. Some of you, I have seen that students solve this different separately and that one separately. It makes it very hard. Then you want to find the common answers. But don't make the problem hard. If that is the case, then do you remember there are two scenarios with plus and minus. If only this one is the case, then I have one 45-degree angle, the other one is 180 minus 45 degree. But because simultaneously they are supposed to be satisfied, those cases, we shouldn't consider them, because then there is only one possibility, and that is 45 degrees, of course, plus any multiple of 360 degrees. I want you to see that why I am deviating from the standard way. In the standard way, for example, if this one is only given to you in chapter 2, this is not the only answer. Another answer for cosine, it will be plus or minus. If this one is only given, this is one answer, the other answer is 180 minus 45. The reason I am not considering those cases because I want to I want to have both of them simultaneously true, and that's the only one. Yes, and I am looking for theta, so I divide everything by 5. It becomes 9 degrees. What about that one? 72 degrees. N belongs to Z. Again, the same story. How many answers I got for theta? I got infinitely many, but how many of them will work, is good for me? Only 5 of them. Why 5? Because the power here is 5. Okay? And the period of this function is exactly 72 degrees because it is 360 degrees divided by 5. And I told you, this is a rule of thumb. So you can just start from 0 only. So n0 up to 1, 2, 3, and maximally 4. In total, I will have 5 options, and 5 is the exact number. So if n is 0, theta is 9 degrees. If n is 1, theta is what? 81 degrees. If n is 2, is what? Another 72, it becomes 153 degrees. If n is 3, theta becomes 225 degrees. And then finally, if it is 4, theta becomes
297.
what?
297.
300?
No, 297.
297, yes. And these are the only numbers. Yeah, let's double check again. So every time I add 72, yes? So 9, this is correct. 72 to that one is also correct. That is also correct. And then 72 here, that's also correct. But what I want you to write down at the end are z's, not thetas. So you have to write 5 of them. So z1, R, what is R? For all of them, R is this weird number, whatever that is. So you write R there. And then cosine of 9 degrees plus I sine of 9 degrees. This is one answer. The second answer is the same absolute value, but cosine of 81 degrees plus I sine of 81 degrees. The next one is the same absolute value, but cosine of 153 degrees plus I sine 153 degrees. And then finally, the other two, z4, is 1 over the 10th root of 2 cosine of 225 degrees plus I, sine of 225 degrees. And then z5 finally is 1 over the 10th root of 2 cosine of 297 degrees plus I sine 297 degrees. These are the answers. And I hope that you are not confused. What is this? This is very complicated. No, it is not complicated. Because if I have calculator available, if I want to stick with the exact values, of course, these are the exact values. But if I want to simplify them up to some decimal points, I just put these numbers in the calculator and calculate something. So it becomes a very simple, innocent, complex number at the end. The only one that we can calculate is which one exactly without calculator?
225.
Yes, 225 is 180 plus 45. So we can use those ideas to calculate this exactly. But the other ones we cannot calculate exactly. We have to use the calculator if we want to do it. Otherwise, we can keep it like this. But again, let us try to analyze this problem geometrically. So where are these rooted? Where are these roots lying on the complex plane? Can I say something about them? All of them lie on the circle centered at the origin, but whose radius is? This is strange number, 1 over the 10th root of 2. And then they, each time I have to rotate them, how many degrees? 72 degrees. And then the vertices form what? A regular pentagon, yes? So if I want to exaggerate a little bit, so let us say that this is the circle. Okay. This number is 1 over the 10th root of 2. This number is negative 1 over the 10th root of 2. Negative 1 over the 10th root of 2. Positive 1 over the 10th root of 2. Okay? But where is the first one? The first one is 9 degrees. So let us say this is 9 degrees. Of course, it is not that easy to draw. Let us say this is the first one. The second one will be 72 degrees more. 72 degrees more is still 81 degrees, so it becomes approximately here. Yes? So it's 1 over the 10th root of 2. So the second one is here. So this is Z1, this is Z2. The third one, what is the argument of the third one? 153. Something like that. I don't know, this should be 72, this should be 72. And then there would be another 72, which becomes what? 225. It becomes exactly in the middle. Yeah, of course, my picture is awful, but this is Z4. And one more here, Z5. What is the angle? 297 degrees. I mean, this is really bad picture, but if you do it precisely and then connect them, it becomes a pentagon. Not only a pentagon, but a regular pentagon, which is not actual. Like, this is not a very good picture at all. But if you draw them precisely, you will see that the vertices will be, these roots will be the vertices of a regular pentagon. Okay? One thing that I want to mention here, for the case of second power, what do you think? What do you expect happens? I mean, for the second power, you can have a shortcut. Can you predict what will happen? For example, if I give you z squared equals to 1, even in the realm of complex numbers, and I ask you to solve this, what are the answers? What? Plus or minus 1. And that is finished. Why? Because if this is 2, there are exactly 2 answers. 1 is one answer, minus 1 is also another answer, and then I have exactly 2 answers, so that's it. Yes? But what do you think about this one? Z squared. So the formula that we had before, do you remember? I take the square root of plus and minus works. But let us say that I have I here. Or let me write minus 1 here. You can solve the problem from scratch using that method, but I'm just talking about the second power. We might have a shortcut, especially if the right-hand side is a real number. So what should I do? What is in this case? What are the answers? First of all, how many answers you expect? 2, because this power is 2. If you guess them, if you can guess 2 of them, then it means you solve the problem. So can you guess 2 of them? One of them is very famous. I. The other one is minus I. Yes? So this idea that plus minus still works in the realm of complex numbers if I have the second power. But then of course, if I ask you z squared is equal to, let us say, square root of 3 plus I. We don't know exactly the answer immediately on top of our head, but we know that they are opposite of each other again. I will have two roots again, but one of them is opposite to the other one. Okay? Do you see why, from geometrical picture, why these two has to be opposite? For example, in this case, there is no reason that this one and that one are opposite, this one and that one are opposite. But for the case of second power, definitely I will get two answers as I expect, but these two answers are opposite to each other. Can you see it from geometrical picture? Yes?
Well, in the polar form, that would mean they're 180 degrees.
Not polar form. Okay, so what does it mean? Because I have two, then I have to divide the full circle 360 degrees to 2. And it becomes 180, 180. No matter where is the first one, the second one will be 180 degrees more than the previous one. So it will become in the opposite. And if it is in the opposite, it means it is minus. So remember that if this is the second power, still the method of plus minus works. But not for the fourth power, you know. If I have fourth power of 16, let me write this one. X to power 4 is 16. In the realm of complex number, in the realm of real numbers, how many answers you get? 2. And those are plus or minus 2. But if I write this equation in the realm of complex numbers, how many answers you will get? 4. 2 of them, of course, are these ones. So we cannot say that they are opposite. But can you tell me something about if they are also opposite or not?
Two of them are opposites, and then two of them.
Pairwise, they are opposite. Why? Because no matter where is the first one, because this is 4, so I have to rotate every time 90 degrees. So when I rotate 90 degrees, I end up here, but when I rotate another 90 degrees, it will become opposite to this. And if I rotate 90 degrees from here, this becomes opposite to that. So if I have z to power 4 from geometrical picture, it is clear that I will have 4 roots pairwise opposite. So this is a good picture to have sometimes. Okay, but let me wait for you and solve this one for me. So z squared is equal to square root of 3 plus I. So find the solutions of this equation. So we want to solve this one. Z squared is equal to square root of 3 plus I. According to what I told you, first of all, you expect exactly two answers, and you expect one of them is opposite to the other one. Yes? But let us really understand that. So you start with what sentence? You say let z be equal to r cosine theta plus I sine theta. Yes? This is a very simple thing. And then you plug this back into this equation and use the formula. So r goes to the power of 2, but instead of putting the power of 2 outside the pair of brackets, 2 will be multiplied by the argument. Okay? And then this becomes equal to what? It becomes to square root of 3 plus I. Then I compare the absolute values. Absolute value on the left becomes r squared. Absolute value on the right becomes the square root of 3 to power 2 plus 1 to power 2. Yes? So r squared becomes equal to 3 plus 1, 4. Square root of 4 is 2. But then r is positive real, by the way. I forgot. I wrote r, but it is always positive and belonging to r. That is a better way to write it. So r is positive and equals to 2 and real. So r becomes only square root of 2, not plus or minus. Be careful. You are not allowed to put plus or minus here because absolute value by its definition is non-negative. And then you go back. R squared is 2 You put 2 here. Oh, this is 2. Yes? It becomes a square root of 3 plus I. And then you divide everything by 2. So cosine 2 theta plus I sine 2 theta becomes equal to square root of 3 over 2 plus 1 over 2I. Yes? Okay, and then you come up with a system. Cosine 2 theta is what? Is the square root of 3 over 2. And then you have sine 2 theta is 1 over 2. I intentionally give the numbers that I have in my memory. If these numbers are not famous, you have to use your calculator, of course. But what is not that number? An angle whose cosine is the square root of 3, whose sine is 1/2. Both of them are positive, so that's in the first quadrant. 30 degrees. So 2 theta becomes 30 degrees plus n times 360 degrees. When I divide, theta becomes 15 degrees plus n times 180 degrees. And n belongs to z. Yes? So what we do, we actually put 0 and 1 only. Okay, so if I put 0, theta becomes 15 degrees. If I put 1, it becomes 195 degrees. And then everything is ready. I put it back into the z. I will get 2 answers. So z1 is r, which is the square root of 2, times cosine of 15 degrees plus I sine of 15 degrees. The other one is z2, square root of 2 cosine of 195 degrees plus I sine 195 degrees. This is not wrong, this is correct, but you might don't see that they are opposite of each other, but they are, yes? Because cosine of 955 is equal to minus cosine of 15, and sine is the same, because they differ by 180 degrees. So if you want, from here and here, you can pull a minus sign out. It becomes minus the square root of 2 cosine of 15 degrees plus I sine 15 degrees. So if you want, you can write the answer z is plus or minus square root of 2 cosine of 15 degrees plus I sine 15 degrees. That's one possible way of writing in which you can see really they are opposite to each other. By the way, I don't know how many of you remember, this is one of those cases we can calculate exactly without calculator. How? Addition and subtraction formulas, yes? Because 15 degrees can be viewed, for example, as 16 degrees minus 45. So then I can use the subtraction formula for cosine and sine to calculate these values exactly. But that is a minor thing, of course. Okay? Okay, so let me also talk finally about the root of an equation of a complex number. This is somehow optional. They don't talk about this very strictly in the book, so I would write optional. So can you let us try to make sense out of it. If I give you a complex number z and I give you a natural number n, what do you think is a good definition for this?
I mean, what we just did here, we used the polar form
No, what is a good definition for it? So if I ask you what is a square root of 2, what is the definition of a square root of 2? Or what is the meaning of this one? They have shown that there exists one unique positive number whose second power is 2. That number is symbolized by this symbol. So in the same sense, z to the power of 1 over n should be the number whose nth power is z. Okay? This is the idea of to define this symbol. We say this is something whose nth power is z. Okay? So then it means that by comparing the formula here, I want to give the role of w to this c, and I want to give the role of this c to this one. Okay? So in principle, if I want to find z to the power of 1 over n, I need to find the solutions of this equation. So yes, I need to find, of course, I have to change the perspective a little bit. Yes? If I can solve this equation, what I get for w, it's a little bit different from this standard one. Here, w was given, z was unknown. Here, w is unknown, z is given. I hope that you agree with me. If I can solve this problem, it is reasonable to call w as the nth root of z. Yes? And then we symbolize it by that. But that's also not hard to understand because, for example, let us say that w is equal to r cosine theta plus I sine theta. Then I put it here, this becomes r to the n, then I have cosine n theta plus I sine n theta. And then let me write z to be another one, so let us say rho, I don't know, cosine phi plus I sine phi. Yes? So instead of z, I write the polar form, instead of w, I write the polar form, and then I compare them. Yes? But it is not hard to see. The left-hand side is supposed to match with the right-hand side, so the absolute value of the left should match with the absolute value on the right. And then I will have a system that cosine n theta should be cosine phi, and sine n theta should be sine phi. Yes? From here, r is the nth root of rho. Yes? And from here, n theta is phi plus n times 360 degrees. But I'm looking for theta, so theta is phi plus n times 360 degrees divided by n. Sorry. Yes, I have to say sorry because this n is not that n. So let me write it k. K is an integer. So we are done. I am looking for w. So w is equal to, instead of r, I put the nth root of rho, cosine of theta. Theta is this number. Plus I sine of that number. But what is k? K runs from 0 to 1 to up to n minus 1. So if you want to know a little bit more, which is very related, by the way, I don't know why they don't talk about the nth root, but that is how we do it. So if I want to summarize this, if I want to summarize that, if you are supposed to find the nth root, I cannot say the nth root anymore, by the way. We can talk about this. I can talk about an nth root, yes? So if a complex number z is in this form, yes, then z to power n is not single valued. There are n different values for this symbol. And if I ask you how you find them, so let me stick to the same notation that I used for z. I used rho here and phi here. Okay, if that is the case, then this symbol is the nth root of rho at the level of real numbers. This is just the famous nth root. And then the argument is not single valued. The argument is this argument that you see divided by n, but not only this one, any multiple of 360 degrees, any integer multiple of 360 degrees, but k, for the same reason, it starts from 1 to up to n minus 1. So if somehow you are interested to know how we can define the nth root of a complex number, again, I say the nth root, that is not correct, an nth root of the complex number. So this makes the problem a little bit hard. I mean, in complex numbers, in real numbers, if I am working with real numbers, if I write this, what is the answer? Let us say I am not working in complex numbers. What is the answer? It's 4 only. But if I want to calculate this in the realm of complex numbers, that is why some people get confused. If you are dealing with this in the world of complex numbers, then you have to write plus or minus 4, because there will be 2 answers. So it depends. That is a matter of confusion. You see, even I have seen many teachers, when they are teaching, working in the real numbers, they say this is plus or minus 4. But this is correct. If you are working in real numbers, this becomes correct if you are working in complex numbers. Of course, this is exactly the same symbol, because a real number can also be viewed as a complex number. So for example, if you see this formula in a complex number book, they don't write ABC formula with plus or minus. In principle, they write minus b plus b squared minus 4ac to the power of 1/2 divided by c, divided by 2a. But this automatically means plus or minus, okay? Because that's the second root. If you are working in the complex numbers, it always should be interpreted as 2 numbers. Yes? This number, so that's what I'm saying. When you write, for example, when I write 16 to power 1/2, and I know that I am in the realm of complex numbers, I have to write plus or minus. So in this symbol, plus or minus is implicit in the formula. But still, many of the complex number books also put plus or minus. But I think that's not correct. You have to make the conventions completely clear. Okay. So if this is the correct version, if I ask you to calculate this, you have to calculate this according to this formula, and then automatically you get 2 answers, 1 plus 4, 1 minus 4. So 16 to power 1/2, I cannot say what is the square root of 16 if I am working the complex numbers, because there are 2 answers. But I can talk about the square root of 16 when I'm working real numbers. You might say, but like still we have 2 numbers whose power is 16, second power is 16. Yes, but there is a convention there. In the real numbers, the second root by convention is the positive one. Okay, so hopefully you are not confused. So you don't need to be worried about that from that part that I called it optional. So you don't need to be worried about that much. Any questions? Yes.
Do we ever use the surge sign with complex numbers?
What?
Do we ever use the surge sign with complex numbers?
Yes, so there is a convention, I like it a lot. So because you know that even though this is a multi-valued function, but one of them is called the principal value. So let us talk about that. We have a little bit of time. So principal value, and that is with 0. So if I choose 0, it gives me the principal value. So the search sign here, it doesn't pose any problem because this is real. So that this search sign is used exactly as the same sense as I'm using the real numbers, but you are right. In the complex numbers, this is my convention and some books sticks to it. I think it's a very nice one. If I write this, I want to differentiate between this symbol in the complex numbers with that. Here, if I use this symbol, I means all of them. But if I use this one in the books that are respecting them, they are referring to exactly one of them, which is the principal one, and is for the case 0. So I really like this convention, because if you use this convention, then there is no matter of confusion. If I talk about this, and by the way, this becomes immediately consistent with this symbol of nth root of rho. Because you see, I am using the search sign, and it means that you have to stick to the principal value. The principal nth root of any real number is the same ordinary nth root of real numbers. So yeah, I like it. So in principle, in real numbers, there is no difference between these two symbols. But in complex numbers, some of the books are following very nice convention that when they use this, they mean any one of those n numbers. But when they use this, they mean exactly the one which corresponds to k equals to 0. And that is common to all complex numbers books. That is called the principal value. And that is why dealing with complex functions is a little bit hard. So for example, what is the problem of this? Can I say I have this function? So let me write 1 over 3. Do you agree that this is not a function? It's multi-valued, and some complex numbers call it a multi-valued function, but that's complete misnomer, because the essence of a function is that not being multi-valued, But that's why, for example, but if you stick to this convention, then this is really a function, because it gives you exactly only the principal value. But these kinds of messy things you can see even in the books. Yes. So complex numbers books are very comfortable to talk about multi-valued functions. So that's what it is. And of course, they can restrict the multi-valued function in a way that it becomes a unique valued function, and those are called branches of the functions. That becomes a little bit more complicated. But yeah, that is what it is. But of course, they found a way to make sense of all of this, so they can talk about limits, derivatives, integrals, and everything. Yes.
Are multi-valued functions not really a thing?
No, multi-valued function is complete misnomer, because what is the meaning of a function? A function, it means that you have two collection of items,
This is like
and then from each one of them in the domain, there should come one and exactly one arrow out. Yes? So for example, this is valid for a function. This is valid, but this is not valid. Because from here, I have assigned two different values to the same value. And that's exactly what's happening. When I calculate this, it means that when I give you z, that z goes to more than one object. So it is not a function at all.
I've heard the word multi-valued function used.
So I don't know what is this multi-valued function used exactly exactly for this case, that you can assign more values to one single value. But I mean, it is not a good name, because when we talk about functions, when I teach functions, we emphasize on the fact that it should be single valued, Okay. Any questions? Okay, so this lesson is finished here. The next lesson I will upload it on the YouTube so you can check it tomorrow. But there will be one more topic left, which is not directly related to complex numbers, and that is equations with higher degrees. Some of them are related to the complex numbers, but that can be viewed as a different topic. But of course, it is in this chapter, and I have skipped that. So next time, I will finish that one. And I think it is better to have 2 quizzes for the complex numbers because that's important. So I will break it into 2 parts, and then we will have 2 quizzes for that. And of course, the topic of integrals are left. We have to go back and cover that one as well. Okay, so I stop here.